Let's continue our conversation about rotations. And in this segment, I want to introduce Newton's second law for rotations. The nice thing is, we've already been thinking about Newton's second law a whole lot. Recall that Newton's second law is a cause and effect relationship. What do forces cause? They cause accelerations. How much acceleration do I get? It depends on how much mass or how much inertia I have. Now, Newton's second law for rotations is very similar, right? What causes something to rotate? Torques. So it is a cause and effect relationship also. Torque is the cause, angular acceleration is the effect. So torque is the cause, changes in rotational motion are the effect. And here's my bicycle wheel. If I apply a torque, its rotational motion changes. Well, how much does it change by? Well, it depends on the torque I apply and the moment of inertia of the wheel, right? If I apply my force right here at the center, how much does the rotational motion of the wheel change? Not at all, because a force applied at the pivot point does not create a torque. If I apply a force right here, then I get a certain change in the rotational motion. The same force applied out here gives a greater change in the rotational motion because it's a greater torque. Okay, so forces cause accelerations, torques cause angular accelerations. I'm going to go wash the grease off of my hand. I'll be right back. So you could probably come up with Newton's second law for rotations right now, right? What is a force in a rotational sense? Well, that is a torque. A force is a push or a pull. A torque is a push or a pull in a rotational sense. What's our rotational analog to the inertia? Well, it is the moment of inertia. M is the inertia, and I is the moment of inertia. What is our rotational analog to acceleration? It is angular acceleration. So, this is Newton's second law for rotational motion. And it is also a vector equation. We've left the vector signs off of here because we take a simplified approach to the vector nature of torques and rotational things, where we only deal with clockwise and counterclockwise. And it's an effective way to treat this in an introductory class. But that's why I haven't included the vector signs here, because we don't really go full in depth in the vector nature of torques. So when I give you some Newton's second law rotational torque problem, and we can identify it as a dynamic situation. In other words, we can identify that there is some angular acceleration happening. In other words, it is not an equilibrium situation, which we're going to talk a whole bunch about in the next chapter. Then here are a nice set of steps for solving those problems. Once we can identify it as a Newton's second law problem for rotations, we should draw the system. And we're not using the particle model anymore, right? We care where forces are applied. So we actually need to draw out the whole situation more than just a dot. And we draw the forces on the objects where they act. I'm going to encourage you to continue to use the conventions that we've been working with this whole time, right? Force vectors should point away from the object. The tail of the force vector should be at the location where the force is applied. We should identify the pivot point and pick a positive direction. So the pivot point in these problems will generally be pretty obvious. In the next chapter, when we start talking about rotation, or when we start talking about equilibrium and torques, then it won't necessarily be obvious. But it's really important to go through the process of saying, where is the pivot? Most of the time, the problem will make it clear where the pivot is, but it's still really important that you go through that process. Identify where the pivot is, because torques, moments of inertia, everything depends on where that pivot is. And unless we have a compelling reason to do otherwise, call counterclockwise positive. And finally, we apply Newton's second law for rotations and we solve. And much like with linear force problems, Newton's second law problems for rotations are similar in that we have to make the equation that we're going to solve for what we're looking for, right? It's not a situation where we hunt for the equation and plug in our knowns and solve for the unknown. It is a situation where we have to create the equation that we plug our unknowns into. Okay, let's just try an example. A baseball bat has a mass of 0.82 kilograms and is 0.86 meters long. It's held vertically and then allowed to fall. What is the bat's angular acceleration when it has reached 20 degrees from the vertical? And it says we're supposed to model the bat as a uniform cylinder. So this is obviously not a bat. It is a pipe, but that's okay. This is the situation. Okay. What is its angular acceleration when it is 20 degrees from vertical? So right about here. Right, so I let it fall. What's its angular acceleration at this point? That's what it's asking. Okay, let's do a quick sketch. Okay, there's my baseball bat. Where's it? Where's the pivot? Doesn't really tell us, does it? But if my baseball bat's falling, isn't it pivoting about this point right here? So I think my pivot is down here. Let's just identify it as its length is L, which they gave us, right? L equals, 0.86. And then they gave us the mass. Okay. What's our next step? Let's see. We drew the system. We need to draw the forces on the object where they act. So I see two forces acting on here. There's the weight and a normal force, isn't there? Where should we draw the weight acting? A lot of times I see students draw the weight acting out here. Ooh, but all of the weight is not acting out here. Where is the weight acting? Is it all acting right here? No. This is this point we call the center of gravity. We should draw the weight acting at the center of gravity. Where is that? Well, it would be right in the middle, right? The center of gravity of a uniform object is right in the middle. Now, in a real bat, the center of gravity would be closer to the fat end than to the skinny end. But it says model the bat as a uniform cylinder. And any uniform object has its center of gravity in the center. And so we should draw the weight acting at the center of gravity. And my drawing's getting a little cluttered. Let's move L for now. There's W. Okay. Other force, normal. Where's the normal force acting? Well, the normal force is acting at the pivot, isn't it? And we'll see here in a minute that this is not really going to contribute to the net torque. We'll talk more about that in just a second. Great. So now I have defined all of I've drawn my forces, where they act. My next step is I should pick a pivot point. Well, we actually already talked about that. So here's my pivot point. And we should decide what direction's positive. This is going to be accelerating in a clockwise sense. We could make that positive if we wanted to, and then we'd get a positive value for our alpha. But, and there's nothing wrong with that. I'm going to go ahead and stick with our convention, right? Our convention is counterclockwise is positive. So I'll just go ahead and stick with that. Okay, now we are supposed to apply Newton's second law. So torque net equals I times alpha. Okay, and we're going to be, so a lot of times one thing that trips students up is when we do these Newton's second law problems, it's an interaction between two different things, right? We've got Newton's second law, which tell us what torques do, and we have the definition of torque, which tell us what torques are, right? So in other words, we might have, this is just for any individual force, what is the torque created by that force? And then if there's multiple forces, we might have to put this into here several times, right, in order to find the net torque. Okay, so let's just go ahead and do this. I see two different forces here. And let's go ahead and let's start with the normal force. Well, the normal force. What does R mean in this equation? Many of you just thought in your brain, the radius. You're not wrong. I don't see any round things here, though, so maybe you are a little bit wrong. If there's no round thing, there's no radius, so it can't just be the radius. What it means is the distance from the pivot to where the force is applied. So, how far is it from the pivot to where the force is applied for the normal force? 0. So the normal force creates no torque because R is 0. So, So we don't have to worry about the normal force creating any torque, so it doesn't show up in this equation. Once you get good at a few of these, you just won't even have to draw any forces that are applied right at the pivot point. So we have the weight. Is the weight creating a torque? Oh, absolutely. It definitely is. It definitely is. So the problem tells us that this is 20 degrees. That means that this is also 20 degrees. Torque net then, we're going to plug in our definition of torque applied to the W here. So what is our R? Well, for the weight force, R is L over 2 because the weight is applied at the center of gravity. Force, that's our W. Sine of phi. Phi is the angle between R and F. Here's R, here's F. That angle is 20 degrees. Is it positive or negative? It is negative in my coordinate system. Since N creates no torque, this is the net torque. I am done with that. Remember, Newton's second law is instructions. It says take all the torques, add them up, set them equal to I times alpha. What is I? Well, this is a uniform cylinder. What we should do is we should look it up in that chart that I posted in the previous PowerPoint. Here it is. Which one of these is a uniform cylinder? It's this one right here. It is a thin rod. Notice they've drawn this as a rectangular cross-section, but it says of any cross-section, which means that this would apply to a round cross-section as well. So it would apply to our bat. So that is what we should use for our moment of inertia. That goes right here. Okay, so now I've plugged in for my moment of inertia and times alpha. Great. Let's go ahead and do a little bit of algebra, and we can just solve for alpha. Notice one of my L's cancels. If we were to write W as mg, eraser algebra, not usually a very good idea, but in this case we're just swapping out W for mg. I feel all right about it. My m's cancel, and I can solve for alpha. I get negative 3/2 g. Okay, so doing my algebra, I get alpha equals this business here. And now I can plug in my numbers. I get 5.9 radians. Negative because it's accelerating in a clockwise sense. Okay, so there's some interesting physics here. It's interesting that the L does not cancel out. This helps us to understand a demo that I did in the previous lecture, right? You cannot balance a pencil on your finger, but something just slightly longer, and you can. Right? Because the angular acceleration is inversely proportional to the length. So, the larger, the longer the rod, the smaller its angular acceleration.